I can talk about the new plans to make another version, new version of the 8.11 Mac model. The explicit goals of facilitating experimentation and contributions. So, what are our goals? So ideally, we would like to have a Wi-Fi Mac model which is reasonably full-featured, so it has the features of the standards which are widely used or upcoming or even planned. So I listed a few of them: fragmentation, ADCI, block acknowledgement, high throughput extensions, and so on. And it should allow experimentation, so we'd like to be able to configure it in different ways, and it should be hackable also, so people can try out different modifications to algorithms and so on. And even more important, it should allow experimentation and experimental features to be incorporated in the code without putting validity at risk. So when we have an implementation, a model implementation, which has been validated by somebody and it's proven to be good, we don't want to risk this asset, that it's valid. And still we have to allow experimentation. So it looks like a different question how to do this. So basically the answer is we have to use a modular plugin architecture. Why? So if there's a significant part of the model, the MAC protocol, which is pluggable and it has multiple implementations like these ones, then if you are using, for example, one of the green blocks, then you can have some other people hack away on the other blocks and it won't interfere with you. So if the green blocks are validated, then other people can go work on these ones. You will not be disturbed. Then, also, if you have a project which doesn't require all the features, the latest features of the MAC protocol, then you can just use the simplest implementation that suits your project. And the other more complex, you will not get the bugs from the other and the performance penalty from the other more complex implementation. And this kind of plugin architecture also helps contributions, because people can copy one of these blocks, put in experimental features, and we can accept it into the INET code base and label it as experimental, stuff like that, and then people will know that, okay, we have to treat this with caution. And if somebody needs to be sure that simulation results are valid, they can still use the trusted blocks. Yes, and it also makes things easier for us INET maintainers, because if the contributions comes for the experimental things, we can just accept the pull request and check it in and not bother too much, because, well, that's experimental code. So, what are the problems with the current Mac implementation? Well, there are tons of missing features that everybody knows. Okay, it's monolithic, it's single class. So if you change anything in it, everyone will be affected, and validity is put at risk. And it's also difficult to maintain and extend. Why? Because it has a complicated logic. So for example, inside the class there's a huge state. So there are 7 data members, and they are all updated in all parts of the code. So the whole thing is very difficult to understand and reason about. And the state machine it has like 7 states, but it has 50 transitions. So it's also very, very difficult to comprehend. This is what a state machine looks like currently. We drew it with graph bits, and you can see that it's you can see that it implements multicast, CTS, RTS, and probably ADCI from the states, but there's so many transitions are really hard to comprehend. So how this state came about, and what are the reasons that it looks like this? Part of the problem is that the state machine and the code mixes two kinds of aspects. One aspect is accessing the channel, so like interframe spacing and backoff and this kind of things. And the other things is how different MAC protocols exchange frames, dialogue between them. So like acknowledge frames, CTS, RTS, CTS, block acknowledgement, these kind of frames. And when you combine these two together in the same state machine, then you get the Cartesian product, so if the state number of states grows, and then you can compact back these to a smaller number of states by introducing new state variables. So this is why why we have 70 state variables and like 7 states. But you can imagine that if we introduce like one more state, one more variable to store the current state, and we could do the same thing with one state and even more transitions at the cost of extra one variable. So actually the number of states doesn't mean much. The complexity is still there. That's the problem. So we try to overcome the problem. Well, okay. So what were the key ideas? The thing is that we have to decouple the transmission process, so the channel access process, from receive process and from frame exchanges. And actually we were reinforced in this idea because there is an SDL, a formal description in the standard, and that also uses different processes for transmission and reception and even for backoff and for tons of different things, which all these processes do just execute in parallel and keep in touch via signals. So that's the basic design. And also we'd like to use frame exchanges as building blocks, like data plus acknowledgement or RTS plus CTS, and there are more complicated exchanges in the later revisions of the standard. Yes, and also like good C++ design, so many features can be just encapsulated into C++ classes. So here's the basic architecture. It is just a concept, so I think this workshop is a perfect timing. We just have a design which is detailed enough to be presented, but it's not yet elaborated to the point that it cannot be changed. So we can still accommodate feedback. So the basic thing is that we have 2 layers here. The lower layer deals with channel access, and the upper deals with exchanging frames. So we have here we have the classic transmit process. It takes a frame from the upper part, and transmits it over the channel using the channel access protocol, the medium access protocol. There are 4 of them because in the E revision of protocol we have traffic classes and access categories and so on. Okay, there we have reception, which basically receives the frame from the physical layer, and it checks the checksum of the frame, and if it's not valid, then discards the frame, otherwise it sends it up. And it also maintains the network allocation vector, which is like, those of you who are not familiar with it, it's basically the end of the time until the channel is reserved by the sender. Yes, okay, and in the upper part we'll have the queues, fragmentation, and everything that's built on top of the channel access. So the transmit process. So basically, what we observed by reading the standard is that the transmit that there are basically 2 kinds of transmissions. One is transmitting a contention frame, whereas you need a interframe space at the beginning, and then some backoff interval, and then you transmit the frame. Or there is some slight complication that if we receive a frame with a bad checksum, then we need to switch to a larger interframe space. This is the other one. So that's why there's transmit with contention frame, and there's another one, transmit immediate frame. This is for acknowledgement, for example, where we just blindly wait for an interface frame space and then transmit, and we don't listen to the channel at all. So everything is built from these 2 primitives. And then, okay, we want this process to report back when it's done. And of course, it is from the reception process, it receives the channel state because it needs to sense the channel, needs to be notified when a bad frame has arrived, the DROM checksum, and then it transmits over the radio. So they are basically the interfaces of this process. And that's the state machine. And it's pretty straightforward. It's kind of linear state machine. It stays in idle. When it receives a frame for transmission, it goes to wait interframe space. When it's done, it goes to backoff. When backoff is done, it goes to transmitting. It's complete, it goes back to idle. And okay, when during waiting, sometime we sense the busy channel, then we just go back to defer, and from defer we start it all over. There's one thing, if we're interrupted in the backoff state, then we remember the remaining backoff time, so we use it next time. It's quite simple. It's quite simple. You can notice that the transmission process doesn't contain the acknowledgement or the exponential backoff procedure because we are doing it somewhere else. We don't want to do it here. Okay, transmit immediate frame is just very simple. We wait interframe space and then we transmit the frame and so on, and that's it. Okay, so why we took away the acknowledgement RTS CTS handling from the transmission state machine? It's because in the early revisions of the standards things were quite simple, and when we got to later revisions to N and later ones, there are more complicated frame exchanges, and we don't want to incorporate them into the state machine because then things just get like unmanageable. So today we have like TX, so transmission opportunities, block X sequences, reverse direction frame exchange, and these kind of things. And if we take them into the transmission state machine, it just blows up. Well, EDCA, we just create 4 instances of the TX process, 1 for each access category. Okay, the reception process, it's very simple. It just checks the frame checksum and maintains the network allocation vector, which is basically the time until which the sender has reserved the channel. And it sends up the frames that were received and notifies the transition processes about what happens. Okay, this is the upper part. Well, this upper mech, the name itself, we don't like the name, I don't like the name, but like, I couldn't really think of anything better, so if you have a suggestion, that would be very welcome. It's kind of awkward, but it's a working name. Anyway, so basically it keeps in touch with the upper layers, receives frames to be queued for transmission, and when some frame arrives and it's assembled from its fragments, it's sent up to higher layers. And then, on the other hand, it receives those frames from lower layers, from the reception process, and then it can do 2 things. It can transmit contention frame, transmit immediate frame. That's it. So why is this good? So actually, it means we can deal with just exchanging frames with our peers. And we don't need to care about channel access. We don't need to care about interframe spaces and this busy channel, not busy channel. It's just nuisance anyway. It reduces the complexity. And we can make this replaceable. So we can have several instances of this. Simple ones, more complicated ones, even more complicated ones, experimental ones, and so on. And this thing, we can also make it modular itself. So we can build it up from smaller components. Then it will be easier to maintain, and we can use parts of it, different versions. So we use frame exchanges as a building block. So like a frame exchange actually a C++ class. So we just encapsulate one kind of a frame exchange into a class. So a frame exchange is created as a response to incoming frames received from the upper layer. For example, we receive a data frame, then we can create a data plus ECK frame exchange, which will manage sending a data frame by expecting immediate acknowledgement. We encapsulate it into a frame exchange. Okay, they can be composable. Yes. some examples: data acknowledgement, RTS, CTS, okay, block acknowledgement protocol, reverse direction frame exchange, and okay, frame exchange can span like one TX op or multiple TX ops. Yeah, it has the interface is that it's created by the frame exchange created by the upper Mac, and it's started by the upper Mac, and reports back when it's done, either successfully or not successfully. And what can it do? It can do also transmit contention frames, transmit immediate frames, and be notified about lower frames, and so on. For example, let's look at data plus egg. Basically, you can implement it with a state machine. It's a very simple linear state machine. Okay, we transmit the data, this data, we wait for acknowledgement, and if it comes within timeout, then success. Okay, if it doesn't come within timeout, then we have to go back. We double the backoff interval and try again. And we use this transmit contention frame. You remember this transmit contention frame accepts the contention window as a parameter. So we just double the contention window, we try again, and so on. If we tried enough times and still didn't succeed, then we go to failure. Okay, let's look at a more complicated frame exchange. Like we send RTS, expect CTS, send data, expect acknowledgement. So we can describe it as a sequence of send and expect steps. So this lends the idea that why not create a base class that can do these concepts directly. And basically that's the code. It looks like a lot of code, but it's quite straightforward if you look at it. Basically, we have integer steps like 1, 2, 3, 4. This is do step function. It says in the first step, transmit a contention frame, which is an RTS frame. Okay, when it's done, when we successfully got through this step, then we go to step 1. We expect a reply, which is a CTS. We'll look at it later. When it's done, we transmit immediate frame, which is the data frame, and then we expect an ACK. Okay, and the other two functions deal with like how to do exceptional cases. So, for example, if there is a timeout in this step 1, where we accepted a CTS frame, if CTS frame doesn't come, then we increase the retry variables, like bigger backoff time, backoff window, and so on, and we go back to this step. And in the third step, if the acknowledgement doesn't come, then we just declare that okay, this state machine, this frame exchange has failed. And okay, this process reply thing, it says okay, when we expect the reply here, then we expect the CTS frame, and here we expect an ACK frame. So basically, this is all you have to do for this kind of frame exchange. And you can imagine that more complicated frame exchanges can be also like described quite in a compact way. Yes. Okay. So if you look at C++ class design, there are some more opportunities for good design. We can encapsulate fragmentation, MSDU aggregation, PDU aggregation, these kind of things into C++ classes, rate control, and also like frame exchange selection policy, because in later revisions of the standard, if you want to send a data frame, you have tons of possibilities to choose from. You can use black acknowledgement, not use black block acknowledgement, or and several variations on this. When to send block acknowledgement request, when not to send it, just countless. And it's all up to policy. It's all up to policy. So what's the status? Yes, there is we have some code which sort of works. And the plan is to implement multiple upper Macs. So basically, there are the easier ones we'd like to implement ourselves, just to see that the concept actually is sound and it works. And once that's done, we hope that the committee will like the design, and some people will like add new ones. So that's it. Thank you.
Are there questions for Andras? Or comments on the architecture?
Yes.
So I guess I actually have a couple of questions. How does this interact with the radio state?
Mm-hmm.
So I think for most of the current or for many of the current implementations, there's some idea that the radio state on, sleeping, off.
Mm-hmm. Mm-hmm.
Is that, do you have a sense of where that would live, or is that will those just be independent messages to a radio module?
Mm-hmm. Mm-hmm.
Because, for example, you can do power saving
Yes.
in 802, let me turn on and off the radio, for example.
Yes, I think in the upper Mac. Okay, so first of all, it's up to policy when we want to put the radio to sleep and when we want to wake it up, and we expect that this will be decided in the upper Mac module, and it will let through these control messages or control signals towards the radio. So it can put the radio to sleep, or it can wake up the radio, and it can switch channels, for example. It can set the data rate and these kind of things in the radio.
Will the lower layers check the radio state before transmitting, or are they relying on the upper layer to make sure they haven't told them to do something?
Mm-hmm. Mm-hmm.
So say, for example, we'll have some part of the upper layer saying, send this packet with some content. Yeah, I'm not sure exactly which slide is the best one to look at.
Yeah, probably the first one.
Probably one of the block diagrams. I guess I'm thinking about the case where, say, some upper layer has told the radio to go to sleep, but there's
Mm-hmm.
a packet in process, for example.
Mm-hmm. Mm-hmm.
And especially if you have a very modular structure in the upper Mac, it's going to be hard to make sure that they coordinate so that there isn't somebody telling them, saying, go to sleep.
Mm-hmm.
Perhaps say, while a packet is in process in some other layer,
Mhm.
does there need to be is there something in this lower layer, for example, saying you need to check the radio state?
Yes, I think it's some details, still will have to be added. Yes, yes. So, for example, yes, we talked about this frame exchanges,
Mhm.
and I think, for example, when the node crashes or sleeps, then it should be possible to cancel the ongoing frame exchanges or reset the state of everything to reset the state of the transmitter. We haven't checked this yet.
Because coming from, depending on the file layer,
Mhm.
it's still a little unclear to me here who talks to some representation of the radio.
Mm-hmm. The transmission. Well, okay, we can, if you're talking about configuring the radio, like going to the right
That would be to
channel.
the file layer only.
Yes, and those messages would just go through. And otherwise, it's, okay, the way it is, if we have several transmitters, then, okay, only one of them should transmit at any given time. But this is basically going to be done automatically, because if one of them switches to transmission mode, then the reception module will immediately signal busy channel. Because so an internal collision between among these blocks is handled exactly like external collisions. So if one of them switches to transmit mode, channel will be busy, so the others will have to back up to go to defer mode until the channel cleans up. Basically, this is the way of EDCA works. So all the access categories are just act like different NICs, basically, using different parameters, different interframe space, and different contention windows. So that's our understanding that these things works out quite automatically. And on the other hand, only you shouldn't give the upper block shouldn't give like 2 frames at the same time to the transmit process. The contract is that, okay, if we say transmit contention frame would transmit immediate frame, then this guy has to wait until the previous transmission has finished. If it just sends a new transmit request, simulation will abort, a session failure, whatever. That's the contract.
Michael wants to add something.
I share Laura's concerns about this handling the radio. I mean, due to modeling 815.4, I usually stumbled upon some errors where some module just shut down the radio into sleep mode, and then in the meantime there was a packet. I'll transmit the packet. Oh, channel is in, radio is in sleep.
Well, that's
Big
implementation
error and
issue.
everything.
I mean,
That's a big implementation issue, but it's also sometimes unclear in it's like the state machines that we
Mhm.
take from the standards. Who should send who to sleep, and when
Mhm.
should a packet arrive and not.
so I don't see
And,
any.
The second thing, this when you transmit it, the channel is immediately busy. What about those protocols that can send and receive at the same time?
802.11 is not a protocol like that. This is an
Actually,
802.11.
Actually, there's a paper about it.
There are people that are doing it
That are being
with
able to
software-defined radio based on 802.11 and other radios. But I mean, if this is a general approach, would you like make it hackable in this case?
Okay,
Or-
just one thing. As Laventa said, we want to make simple things simple
Mhm.
and complicated things possible.
Yeah.
So it's not possible to make code which is like extensible in every direction very, very
Definitely,
easily.
yeah.
You can't do that. Well, you can, but then the code itself will be like hugely complicated
Of
and
course.
run slowly and stuff like that. So this design is designed for the current needs. Current and those needs that we can foresee in the near future. So this can serve us quite well. And otherwise, all the things can be replaced in here. So if you need a different like transmission algorithm, for example, if you want to play with a different transmission algorithm, not with the interface space backup stuff, then you can also replace the transmit block, or you can replace the receive block with something else which does some modified things, as long as you keep the contract.
So those contract and those policies are also replaceable and totally flexible in this case.
Well, the policies are actually fixed otherwise. So these are just abstract C++ class interfaces. Otherwise, you can't do a design. So something has to be fixed. But okay, well, if you replace both sides of the contract, then you can replace the contract itself. But,
Yeah.
yeah. But then you're basically writing something completely new.
One more remark,
Yeah,
Laura?
I just wanted to follow up a little bit more on this radio state, because one of the things that gets kind of messy is when you have the radio state change from transmit to receive.
Uh-huh.
So you have to listen to the channel,
Yeah.
and then you have to switch. I listen to the channel, with receive, I
Yeah.
switch to transmit. And in fact, a lot of the semantics of these interframe spaces, both for 802.15.4 and 802.11, a lot of the semantics for that are kind of messy because those spaces are allowing for those trends. So
Mhm.
a lot, for example, the interframe space for the ACK is you just sent me something. I have to defer my ACK long enough to make sure that you're ready. Did you
Yes.
switch from transmit to
Yes.
receive?
Yes.
And so I'm a little bit curious, again, in the context of where you're modeling the radio, where those state changes are happening, because
Actually-
that's the piece that the battery, to some extent, wants
Yeah.
to know. You can handle the delays on the Mac side, but the actual switching,
Yes.
maybe from a battery perspective, actually the radio knows about.
Well, I think that actually this switching delays,
Mhm.
stuff like that, it's not part of the Mac protocol. It not shouldn't be part of the Mac thing. It's a physical layers thing. So if such a delay exists, such a switching time exists,
That's what most of the
then it
interfaces
should be
are
part
for.
of the physical. It should be part of the radio model.
So they are.
Yes, it is part.
It is part of
It is part of the radio model.
Yeah.
Yes, and then it means that, okay, if transmission finished, then the physical layer will probably go to a switching state for a while, and then start sensing the channel only afterwards. So basically, then the reception process should be notified about all these things.
I think
Yeah.
she's right about that obviously there must be some kind of component who tells the radio to switch to receive mode, because it's not going to switch back to receiver mode after just finishing the transmission. It's not up to the radio to decide.
Oh, that's
And if the
important
radio is
point.
in
Okay.
transmitting state,
I see.
it transmits the signal, and it just waits there whether if it needs to transmit another signal
Okay.
or just switch back to receive mode. It's up to the Mac to decide.
Yeah, that's a good point.
And it must be put somewhere. I guess it must be put into the exchange class, because the exchange class knows when to start to transmit something and when to expect some reply. I think I would put it there somewhere. And regarding the other question, that whether if it might happen that some exchange just gets into trouble because the radio is turned off, for example, and it wants to transmit a message which is obviously not possible on the radio, we'll just throw an exception and the whole simulation will abort. I think it's pretty easy to do this, that only the guy who's responsible for controlling the radio, putting into off state, or he just has to talk with this other guy who is driving the exchange. So it's not that difficult. Obviously, you're right that we have to think about it, because it's right now it's missing. It's missing.
Does the
So it's a good point.
Does the PHY own it? Does the radio own it? Does the Mac own it? Who's going to be responsible for?
I think it's
not complicated,
part of the
somebody has
outcome.
to be
I think
somebody-
both things are part of it.
Yeah,
Mhm.
yeah, I don't know if you just
Think
want to
so.
say that there's a default idle state, and as soon as you finish any operation, I think that's what most radios do. So you transmit or you receive, and then you just, when you're done, you go, I don't know.
That's
what-
right, but it's not
It's-
up to the radio to decide, because
It's
it
up-
takes time. So if the radio would ultimately switch back to receive mode, it
But
takes
the radio
time.
would say, I'm now transitioning, I'm in state transition,
Yes,
and
I-
then it would end up in the correct state, and then you could send a notification back.
Yeah, I think it
that's
works.
I think that's how the SCL is defined, but I could be wrong. I think the SCL is defined in terms of the
I
radio.
think the radio sends back the message that transmission is completed.
Transition, yeah.
But it still doesn't mean that the radio
Switch this.
electronic is going to switch to receiver mode,
Yeah, I
because
don't
it
know
takes
whether-
time.
Yeah,
So
it
if-
takes time, but I'm not sure whether it does it, whether you model that it does it by default, that it takes time, but it's, so after it's done transmitting, it says I'm going into transition, some logically transition state, and then signals that it's completed going back to
I think
idle.
that's the way.
I think, it's just a question, who should own keeping, who should own
That's a good
keeping
question,
track of
because it's missing. So I mean, it's not in the current architecture, but it must be there somewhere, because
Because you definitely need
Because
those
power
switching-
consumption
you definitely-
is-
even if you're not doing sleep, you definitely need those switching delays to be correct, because that's the whole semantics of the IFS, that's what they're based on.
Mhm. Well, there are some further questions that need to be thought about. That I kind of love that, for example, if we use EDCI, then this, if we have an internal collision, then okay, if they want to transmit at if different access categories want to transmit different times, then internal collision will, like the bidirectional feedback will prevent the later ones from transmitting, that's okay. But when they want to transmit exactly at the same time, because random numbers are like that, then the one with the highest access category has to win. And this is like, the simulation algorithm will have events, basically several events at the same simulation time, and it will only by chance who wins. So we'll have to resolve this situation somehow. So there will be some complications in the design due to that. Another thing is, I heard from David that if we have many Mac instances, then it's not a good idea to have many timers. So currently design uses like one timer for each transmitter. So like, but we can also divide it by 4, so you can use a common timer with some juggling around in the surrounding Mac module class. So like reuse timers.
Just
We
one
can
time.
get rid of decrease the number of necessary timers by some.
But there are,
clever
like in reality, a couple of timers running, so, I mean, you retry a couple of times your transmission. If a channel is always blocked, eventually you have to signal up. If you transmit it and you get some errors whatsoever, you have to eventually signal again. And there are a couple of times running, and depending on that, there are different reactions going in the upper layers.
Mhm.
So I don't know if you can abstract everything into one timer, because
That's
the
only
handling of
technical
this one
thing,
timer
because
is-
okay, it's just general question. You have one module which schedules 1,000 timers.
Yeah.
And how can you do it with like one timer? It's a simple technical problem. If you have like a very naive implementation, if you have a list of the timeout periods, you just always schedule the C message for the first one. And when that timer expires, you take the next one and schedule to that, and stuff like that. The only technical thing is you have to do it efficiently, so you keep those time values in some data structure which is suitable for the purpose. So like some priority queue, some binary heap. Binary heap is probably the best one. So it's really a technical
It's like
thing.
private future event set.
Yeah, yes,
Yeah,
a local
exactly.
future
We
event
were
set,
talking
basically.
about it. This could be
I think already had some
feature of
model,
OMNeT.
like in the FreeBSD model somewhere. We already had a timer manager, which is like a local class, and it's able to implement many timeouts just using just one C message.
I think that's a general good
So it's-
feature, not only for
Yeah.
802.11,
Yeah.
but for
So this is
different
pure-
protocols all over the world.
Yeah, so it's just technical, probably independent of the Mac design.
That will probably even solve the problem of internal collisions, I think.
Yeah,
Because just you are
Actually, yes.
just sorting the
Because you are in control.
yes,
In
we are in
control
control
of
of the FES, yes.
But maybe
Yeah.
maybe the priorities also enough.
Yes, we use access priority, yes. Yes.
Yeah, you could have just one timer for the entire TX section, even if it's
Yeah.
not the queues, and then you just schedule the timer for the first packet you think is ready to send.
Mhm.
Then you check if there are TX ops for any other queue,
Yeah.
and if that's the case, you do the internal collision thing, you increase the contention window and stuff like that. So if you have one timer that fixes, like you just said, you can
Mhm.
fixes the problem
Mhm.
of coordination, because you have control.
Uh-huh. For that you mean you would merge the several transmit processes into one block, basically?
Yeah, if you have like one timer and you know, okay, I'm in Q3, that's the next queue that's gonna TX3 in this example.
Because I remember that's how you did it in the code.
Yeah, that's how we did it.
Yeah, no problem.
But then again, our main Mac has fewer features, so you might not, you need more than one timer maybe for that. Because you have
Well, actually, the whole idea is to keep this guy relatively unchanged. So we have
I
one.
think one timer means merging the state together, so it's not certainly a good idea.
Yeah, well, yes.
I think that's what you're thinking, right?
Mhm.
Yeah, really good.
Yes, but also it is maybe permissible to merge, to let these guys get a little bit more complicated, because don't want to, the complexity is not there, and that's not the part that we want to touch later. So if the implementation gets a little complicated, doesn't matter so much. Well, okay, we have to balance things here.
There's one more,
I guess I had one comment. Can you please back up the code with the steps? That was supposed to be RTS, CTS? You had a bunch of switches based on what step you were in. I think it was further, yes, there. So here, to me this looks a little bit odd, because pedagogically, you have to keep jumping. You look for case 1 in a bunch of different places. And then you look for case 2 in a bunch of different places.
Okay, this is basically, if you look at it, this is basically a state machine.
Right.
Only I tried to, so you could actually describe the whole thing with a state machine.
Yeah.
The code would be like a lot longer, and which means a longer amount of code to be read by someone, to be understood by someone. So this is just another representation of the state machine, which we think is probably easier to understand, and we can all manage the corner cases. So basically, this is like if anything bad happens, then the base class would throw an error by itself. So if, for example, the base class could ensure that if we want to send a frame, there's at the same time there are no other transmissions undergoing to just assert. Or Yeah.
I think one point that we like this approach is that if you look at the do-stat function, the cases correspond exactly to the standard,
To this-
to this
to
sequence
steps.
of frames
Yeah,
we
but then
exchange.
the process reply looks a little bit more confusing because you're like, okay, you've gotten a reply. Oh, which of the steps was that associated with?
With steps. Like,
With-
okay, if you're looking at it for reply here, then it's.
So you kind of have to match the expect replies with the process replies. And then some things get matched with timeouts and some things don't.
Yeah, it's a limitation to C++. I mean,
Yeah.
I mean,
It would be
you could
nice.
also return a lambda function
Yeah, it
which
would be
decide
nice.
which accepts the packet and it returns a boolean and stuff
Right.
like that. It would be well like some C++ experts would like it much better because we have this lambda syntax and it looks very nice and very geeky and stuff like that.
I guess to me this still looks a little bit confusing, but perhaps it is just to understand the idea behind it a little bit
Yeah.
more.
Well, I really think that we have to optimize for readability because the code is going to be read by a lot of people. It has to be easily understood by a lot of people. If we want it that people can copy it and hack it and modify it or verify how it works, understand, reason about
I
it,
guess
then
it's
we
just
have to
that
keep.
my first impression is that grabbing all those process replies and putting them in the same place feels like you're taking some kind of disparate functionality and it feels kind of less linear. You're saying, oh, there's a reply.
Yeah, it would be nice
You can get a
to-
reply about CTSs, you can get a reply about ACKs, and then you can
Yes.
get your.
You're right,
That's
it
the
would
part
be
that
nice
feels a little bit confusing in trying to read this code.
to have these three functions merged into one.
Just as a first impression, you have all kinds of different replies that are in the same handler, and there's not necessarily a lot of logical relationship between them, so you have to separate them back out for what the replies came from. And that feels a little bit confusing to me, but perhaps it's
Mhm.
just from not seeing this structure before.
Well, basically the reality is that you have to expect it in C++ code, in readable C++ code, and then you can choose different alternatives, and then you have to choose one of them, which is the best for some reason. And yeah, I agree that it's not nice that, okay, expected lies here, and then the condition whether a frame is expectable, frame is okay as a reply, it's a separate place, and timeout handling is at the third place. But if you want to merge them into a single one, then
Yeah,
basically you have to return functions actions that need to be done.
Yeah,
when something
yeah,
happens.
it may be that this is the best alternative, but this looks a little confusing
Yeah.
to me.
So we could
Just from the first
we
impression.
could return like function pointers or C++ lambdas to decide which decide whether a reply is okay or which specify what to do at a timeout, but that would be probably less understandable. Or I don't know, maybe there are some other ways.
Or we should do another version which uses state machine, and then I think
Or use
it
state
would be
machine,
more
yes.
close to what you expect.
Well, I wonder if it would even just be, I wonder if it would actually be more clear if you separated out the replies and the timeouts. Because right now you kind of have an expect reply with a timeout, and that means that you can get either the reply or the timeout.
Mhm.
And I'm wondering if somehow separating that so you can say, where you can make more clear that you might get a reply or you might get a timeout, and put those two together. In some way, I guess in some way what I'd like to see is in that process reply and process timeout, I'd like to see the case ones sitting together, and I'd like to see the case threes sitting
Yeah,
together.
those two could be merged actually. Yeah, like.
Yeah, I think that's the part that's confusing, is that when you have the replies, all sorts of different things go to reply and all sorts of different things go to timeout. Whereas so I guess in that process reply and process timeout, I'd kind of like to see it where they're switched. So everything that goes to case one sits in the same function. Everything that goes to case three sits in the same function. Because
Yeah.
then you're looking at CTSs and ACKs logically together.
Yeah, like if you have like three functions which do three different things, then you can implement the same thing with one function, introducing an operation code. Like okay, and to take a union of the parameters. So we could do it here. It's like okay, like do step and accept an enum,
So I like
which is
do
like
step. I
what
like-
to do,
I like
what to do on reply, what to do, and make a nested switch.
And that's why I want to add that this kind of solution is just one kind of solution. It doesn't scale when you have the more complicated
Oh, yeah,
frame
no,
exchanges
no.
where there are
No.
several
That's why
data
you try to
frames.
keep all the state
You
machines
just
so small.
can't have a
because
finite.
you can do this with a small state
Yeah,
machine.
you can't have a finite number of steps. I mean,
It
what
was,
is there?
it was just a thought
So it's
that,
just- okay.
that it might look a little more readable if all the CTS handling is in one place and all the ACK handling
Yes.
was in one place rather than cheating as timeouts and replies is the
So,
category.
it's such a-
Actually, the thing is that you could implement frame exchanges in many different ways. You just have to stick to these contracts, and then so one doesn't need to do this state-based or frame machine or state machine-based or step-based implementation. You can do it in whatever way.
One last short comment.
Short. Well, coming back to the initial thing that we need a validated model, and when we have this example with the RTS CTS two-step exchange, I know there are lots of solutions where you take the official state machine, like from the charts, from the specs and everything, and then transmit them into code directly to have a validated implementation.
A lot.
Hmm?
Did you say a lot of
Well, there are some.
for 802.11? Because we-
No, but I mean in general, though, you have like a model state machine and you get validated code out of it that exactly does what you modeled before. Not for 802.11, but in general, like. So how are you thinking about the validation and exactly with the way that you just, this code is quite readable, but how is it also validatable?
Well, validation is a completely different issue. I mean, like whichever way you implement a Mac model, it has to be validated. Then when you validate, it doesn't. We don't care anymore how it's implemented. So we need to treat it differently. And well, there are many ways to validate it. So you can do like this packet drill style tool that was presented yesterday.
You
to set
can
up,
do
like,
formal validation,
cases.
that's what
Yes.
some of the some people do when they take like a
Yeah.
model it in UML and then transform it into some other, transform it to a validated form, get the code directly out of it, and then this code is supposed to be validated, but of course this code is much less human readable than the ones that you produce here. So I think it's a bit of a trade-off, having validated code that easily validates through some from
Well, I
other
don't
programs.
think
and
from
then-
UML code you can just generate something that validates the operation. I mean, like how? I haven't seen stuff like that. Well, you can annotate it, but annotate it with different things and you can generate something. But then you add some information which doesn't belong to the UML in the first place. You just write them there. So actually it's not the UML that's used as validation. You just put some data into it. But you could put those data into somewhere else, totally independent from the UML code, and use that for validation.
But I'm thinking about the state machine and like the basic operations, not the code inside, so the creation of the packet, but the basic exchange like RTS, CTS, CSMA, CA.
I can imagine use a packet drill style tool to be used for this. And otherwise, I think like statistical validation could be quite nice. Okay, if we think practically, then how would you validate a model like this? Okay, you take other implementations which are trusted, and you run exactly the same scenarios, and you expect that it will do the same thing. Like it's one way to do it. Basically the cheap way to do it, because then you don't have to go through and manually check that all of the 1 million transmissions are done correctly.
Okay, I think we should transfer the discussions over to the break. Thank you again, and I think we all are looking forward to the second keynote, and I think it's 4:15.
Quarter past, yeah.
So yeah, have a break, and thank you again for the speakers.